Welcome to the RAOB program's Turbulence and Mountain Wave module. If you support aviation interest and have a need to know about atmospheric turbulence, then there is no better sounding program than RAOB. It is the most comprehensive mountain wave turbulence program available, as it provides consistent, realistic turbulence analyses. While all other RAOB equations are derived from sources found in the public domain, RAOB's mountain wave algorithms remain proprietary. However, the science behind RAOB's wave equations can be found in groundbreaking documents by Lyra and Scorer. These documents were printed in the 1940s, with supplemental works by other scientists in the 1950s. The RAOB user manual lists all reference materials and provides several examples. The groundbreaking nature of the Lyra-Scorer studies is threefold. Wave turbulence can simultaneously be defined as a function of vertical wind shear, atmospheric lapse rate, and specific mountain parameters. Until then, and even today, most turbulence algorithms only use one or two of this triad. Many of today's automated analyses use a combination of several methods, where individual methods impose significant restrictions on boundary conditions, lapse rates, wind shears, and terrain shapes. RAOB, on the other hand, has no restrictions. RAOB is the only sounding program that simultaneously integrates the combined effects of all three variables: wind shear, lapse rate, and terrain patterns. It has provided consistent, realistic results for the past 40 years using the same algorithms. With sufficient sounding information and appropriate terrain parameters, RAOB can simulate nearly any observed wave turbulence condition. Okay, let's get started by calling up a typical sounding. We'll open the analysis toolbar and first apply the traditional FAA turbulence algorithm, which is only a function of wind shear. And here we see light and moderate shear layers. Now we'll apply the wave turbulence function, which is a combined function of wind shear, lapse rate, and terrain. Here we see a similar yet different turbulence analysis depiction, with three waves ranging from categories of moderate to severe. Note that the most significant wave turbulence layer is always colored red, while all others are colored orange. Also note the red text below the sounding diagram, which says that the default mountain parameters were used for this analysis. We'll see more about this default mountain layer later, but for now you should know that the default mountain always produces the maximum wave turbulence potential of the atmosphere. If we right-click on the toolbar's Wave button, we see a prompt to load the local mountain, where the local mountain's parameters are listed here. By selecting the Yes option, the local mountain parameters are loaded and the turbulence analysis is updated. And in this case, the local mountain produced only one wave layer of lesser intensity. The local mountain option is available to quickly load a commonly used mountain into the RAOB program. The local mountain is defined in the mountain parameter file called the raob.mtn file. This file can be altered with any text editor, or it can be accessed by the RAOB program from the Edit menu using this Edit Mountain Parameter File option. Here you can see the local mountain parameters, which are identified by the WMO number 0. For more information about how this file works, please see the separate video called Mountain Wave Parameters. Okay, we've reset the mountain parameters to the default mountain, and it's now time to look at the mountain wave screen. We can do this by first selecting the Displays menu, and then the mountain wave option, or just press the F5 key, like this. When initially activated, this display will always plot the predominant wave first, which is the wave with the maximum wavelength. Within the wave column graphic, this is the wave plotted in red. We can see the details of this and other detective waves by using the menu's Waves options, or just click on the wave column like this. Here we see a listing of all waves detected for this sounding. In this case, there are three waves, where the asterisk indicates the wave currently plotted on the diagram. And here we can see that the plotted wave does have the wavelength with the greatest value. This is the predominant wave as indicated here. Additionally, key wave parameters are also displayed on the wave screen. Normally, the predominant wave is the wave level of primary interest. However, in some cases, there may be an incident of concern which occurred at a different level, such as the 700 millibar level. And in this case, there is a secondary wave at this level. It's important to note that secondary waves are only significant if they are fractional wavelengths of the predominant wave. It just so happens that the 700 millibar secondary wave has a wavelength that is exactly 50% of the predominant wave, which is a very good sign that this wave can be significant. The help files and user manual contain more information about these listings. Now we'll take a look at the wind field. The reported sounding winds are plotted along the leftmost column in a purple color. Just to the right is a corresponding column of blue colored winds. These blue winds are always plotted using a direction of 270 degrees because their only purpose is to reflect the wind vectors that are normal to the local mountain ridge axis. And for reference purposes, these normal wind vectors are plotted as if the mountain ridge is always oriented north-south, so the normal wind can always be represented by a west wind. In this case, however, we are still using the default mountain, which has no defined ridge axis, and assumes all winds are normal to the default mountain. It is important to remember that wave turbulence analyses are most accurate when the user provides specific parameters for the mountain of interest. However, if specific mountain parameters are not specified, RAOB then calculates the maximum potential wave with the default mountain. And RAOB does this by using its internal default 1 kilometer high mountain, which always has a half width that is automatically adjusted to the natural wavelength of the airstream. And for this example, here we can see that the default mountain is being used and that 3,281 feet equals a 1 kilometer high mountain. And remember again, for the most accurate wave turbulence analyses, you should enter specific mountain parameters. And here are the basic rules. Here is the ideal setup for mountain wave sounding data. Assuming the airflow is from the west, the optimum location for the sounding is at the base of the subject mountain. You will then need to obtain 3 mountain parameters: the mountain height, the mountain's half width at the mountain's mid-elevation on the upwind side of the mountain, and the orientation of the mountain's ridge axis. And to repeat, note that the mid-elevation half width is defined as the height midway between the elevation of the sounding station and the mountain top. Okay, here is how you manually enter mountain data. You can select the mountains option from the menu bar, or hover the mouse over the green mountain until it highlights, and then click on it. Here you see the mountain data entry form, and as expected, it initially shows that the default mountain is being used. To enter mountain data, just select the Specify Mountain Parameters option, and there you'll see the 3 mountain parameters entry form. For this example, let's enter a single mountain with a height of 9,000 feet, and for the half width, let's use 4 nautical miles. The last parameter is the axis value, which defines the orientation of the mountain ridge. For a north-south mountain range, we can enter either 360 or 180 degrees. For the special case where the mountain is conical, like a volcano, we can enter a value of 0, which we'll use for this case. Remember, before we press the OK button, the default mountain's predominant wave analyses had severe wave turbulence. Its wavelength is 5.81 nautical miles, and the maximum vertical velocity is 4,300 feet per minute. So let's press OK and see what changes. First of all, the default 1 kilometer high mountain is replaced by our 9,000 foot mountain. The 4 nautical mile half width is indicated by this dotted line. Please note that the older RAOB programs did not plot this dotted reference line. Now remember that the prior default mountain always produces the maximum wave potential, but this user-defined mountain only produced 1 wave. Yet the wave is at the same altitude as the default mountain's maximum wave. Not only does it have the same altitude, It also has the same wavelength of 5.81 nautical miles, but it is a weaker wave with a maximum vertical velocity of 1,500 feet per minute instead of the prior 4,300 feet per minute. Please note that mountain parameters that you enter may not reasonably reproduce an observed wave event. One source of error may be that your sounding was not located at the base of the upwind side of the mountain. Another more important reason is that in the real world, mountains are not uniform in size, shape, and orientation. It is because of these irregularities that manual mountain parameter adjustments are often needed. However, by systematically adjusting the mountain parameters until you get a good wave pattern match, you can then reasonably expect those parameters to produce realistic wave patterns for other soundings from that location. Note that at any time you can use this slider, which is located at the bottom of the diagram, to identify any downwind range location and the wave's corresponding vertical velocity. This information can be especially useful for post-analysis and forensic purposes. And to assist with wave documentation, just use this Listings menu option, or just press the spacebar to display a detailed vertical velocity listing. You can even specify the start and end points, including the reported interval. So now let's close the display and reopen the mountains form. This time we'll select the local mountain option. And just like we saw on the previous sounding diagram, this permits quick loading of a predefined set of mountain parameters. And just like we saw on the previous sounding diagram screen, you can use the Edit menu to access the mountain parameter file, from which the local mountain and others are defined. Please see the Mountain Wave Parameters video for more information. So let's open the mountain data form one more time, and this time let's enter a double mountain ridge. We'll start by selecting the Specify Mountain Parameters as before, but this time we'll also select the For Two Mountains option. And now we can enter parameters for two mountains. And here we'll also need to enter the distance between the two mountains, and then plot. Here we see the second mountain is drawn in a blue color, and the individual waveforms are displayed as dotted lines. Green dots for the first mountain and blue dots for the second mountain. The resulting solid red waveform represents the harmonic or resonant wave. Let's call up the mountain data form one last time. If you use this option to save mountain data to file, the mountain parameters will be appended to the sounding data. And then the next time you call up that sounding file, those same mountain parameters will be automatically loaded and analyzed. As with all RAOB diagrams, you can access diagram options simply by right-clicking the mouse like this. The Format tab is pretty much self-explanatory with typical diagram scaling options. The Data Displays tab provides options for data units, while the Wave Decay tab, however, is unique to the Mountain Wave module. Please be aware that this feature is not a meteorological application, but only a mathematical attenuation of the waveform. Its only purpose is to assist the user in replicating observed wave decay observations. Its use is simple. Just activate the option, set the decay rate to a representative percentage, and indicate the number of wavelengths where the decay percentage occurs. Then select Apply. And here we have resulting wave that decays exponentially by 50% at each wavelength. That completes the Turbulence and Mountain Wave module video. Thank you for watching.